Dear students, today I am posting my next video on operational amplifier parameters, which is called as OPAMP parameters, and we will see the specific and important OPAMP parameters. So the topic will be OPAMP parameters, and in that we are going to see what is input offset voltage, input offset current, power supply rejection ratio, that is PSRR, then CMRR, common mode rejection ratio, input impedance, output impedance, gain, gain bandwidth product, and slew rate. So these are important OPAMP parameters. Okay. So let's first start with the input offset voltage. So this voltage, when we are going to speak, okay, for this, the background of OPAMP should be clear to us. Now, the main background of OPAMP was that if you are having a OPAMP and the two inputs of OPAMP, the output will be a differential gain. Output will be differential gain. That means if you see, this is a OPAMP, okay, and here you are going to give at minus terminal, here you are going to give as plus terminal. This is the output. Okay, so this is input voltage V1, this is input voltage V2. So output will be differential gain and difference between the two inputs V2 minus V1. Okay, so this is what we have seen in OPAMP. Okay, now say if your input voltages are zero, if the input voltage, so V1 is equal to 0 and V2 also is equal to 0, then output voltage has to be 0. But sometimes it is seen that due to imbalances in the OPAMP, this output voltage exists, a small value of output voltage exists, even if the input voltages are 0. That means that is called as input offset voltage. Now that offset voltage, whenever you want to use the OPAMP in practical purpose, should be first made 0. Otherwise, that offset voltage will add to your real calculations. And that can be made 0 by connecting a potentiometer between pin number 1 and 5. 1 and 5, you can connect a pot. Okay, so that pot, if you vary, the output voltage will become 0 whenever the input is 0. Okay, so if you see the definition of input offset voltage here, in the ideal OPAMP, when both inputs are at 0 volts, the output should be 0 volts. Okay, it should be 0 volts. But due to imbalances within the device, a small amount of voltage will appear at the output. This extra voltage can be eliminated by giving a small voltage called input offset voltage to the amplifier. Or typically the input offset voltage for a 741 OPAMP is around 1 millivolt. Okay. Now this is a voltage which is due to the imbalances within the device. And that voltage should be made 0 by connecting a pot between pin number 1 and 5. That is, you're giving an extra voltage to eliminate this voltage. And before going into practical application, this voltage should be made 0 so that you get the correct results at the output. Okay, so general speaking, input offset voltage will be a voltage at the output when both the inputs are at 0 volts. Okay, that small voltage at the output which exists when both the inputs are at 0 volt, it is called as input offset voltage. Then what is input offset current? Now in the same form as we have studied voltage, the input offset current is the difference between the two input currents of the OPAMP with the output of 0 volt. Or typically the input offset current for a 741 OPAMP is 20 nanoampere. Okay. Now it is the difference between the bias currents, okay, is known as input offset current. Now, our typical values will go from 3 to 20 nanoampere, and for a bipolar input OPAMP, and for a FET input OPAMP, it can go up to some picoamperes. Okay, but this current exists. It is called as input offset current. It is the difference between the two input currents when the output is at 0 volt. Okay, So this is called as input offset current of op-amp. Then we'll go to see what do we mean by supply voltage rejection ratio, SVRR, or it is also called as power supply rejection ratio, PSRR. The supply voltage rejection ratio, SVRR, refers to the slight change. Just remember this, slight change in input offset voltage per volt change in power supply of the op-amp. Okay. Now the power supply of the op-amp, whatever we are going to put, is called as VCC. Okay. And the offset voltage is called as VOS. Okay. So here if you see, this will be your op-amp. Okay. And this is your inputs, say this is minus plus, this is V2 V1, and here you will get an output. Okay, output should be differential gain multiplied by V1 minus V2, and here you are going to give plus VCC, and here you are going to give minus VEE. Okay, so these are the power supplies are given to the op-amp. Okay, now if you take the ratio of change in input offset voltage, which is a delta VOS named here, upon change in the power supply of op-amp. Okay, so change in input offset voltage per volt change in power supply of the op-amp is called as supply volt rejection ratio. Okay, SVRR. In some features, it is also called as power supply rejection ratio, PSRR. Okay. So for this, your study of input offset voltage should be very clear. What is input offset voltage? And then if you have that ratio of change in input offset voltage to the change in power supply per volt, then it is called as SVRR, supply voltage rejection ratio, or it is also called as power supply rejection ratio, PSRR. Then we'll go to the next one. The fourth one, which is called as CMRR, a common mode rejection ratio. Now here, one thing you have to keep in mind is the op-amp, whatever we are going to use, okay, it will always amplify the difference between the two input voltages. So here if you see, if you have this op-amp, okay, and this is your minus plus, this is V2, this is V1, okay, and the output should be equal to differential gain multiplied by V1 minus V2, difference between the two inputs. Okay. Now say if both the inputs are same, if both the inputs are same, okay, same inputs, so it is called as common input. If both inputs are same, then here V1 minus V2 will become 0. That means output has to be 0. Okay, output has to be 0. That means if both signal are common, input signals are common, the output will be 0. That means it is rejecting when the inputs are common, and it is amplifying when the inputs are having difference. So it will amplify only the difference between the two inputs. If both the inputs are same, the output will be 0, because the difference between the two will be 0. So any common inputs to both the inputs, okay, a common input for the inverting and a common input for the non-inverting. If the inputs for the inverting and non-inverting are same, then the output will be 0. This is the ability of op-amp because it rejects common signals. Okay. So here if you go to see the definition in the note, in op-amp the output voltage is proportional to the difference between the voltages applied to its two input. This is the basic definition of op-amp. When the two input voltages are equally, ideally the output voltage should be 0. That means when the two inputs are equal, the output voltage ideally should be 0. A signal applied to both the input terminals of op-amp is called as common mode signal. Okay, if the same signal is applied to both the terminals of op-amp, it is called as common mode signal. Usually it is an unwanted noise voltage. The ability of an op-amp to suppress these common mode signals is expressed in terms of common mode rejection ratio, CMRR. Now, typically CMRR for a 741 IC op-amp is around 90 decibels. CMRR is given in the form of equation as 20 log to the base 10 or differential voltage gain upon common mode gain. Okay, so you can write this CMRR as 20 log to the base 10. Then you should take a ratio of differential voltage gain upon common voltage gain in decibels. Okay. This will be in a decibel. So it is a log to the base 10 ratio of AD upon AC, that is a differential voltage gain upon common mode voltage gain. So, okay. So 20 log to the base 10 AD upon AC will be your CMRR. This is how you calculate CMRR value. Okay. Then we'll go to see what is input impedance for an op-amp. Now, input impedance will be like your impedance of the input circuit. And for that, you should know what is the input voltage and input current. And if you take the ratio of input voltage upon input current, it will give you the input impedance. Okay. So here, according to the definition, input impedance is the ratio of input voltage to input current and is assumed to be infinite. It is assumed to be infinite. It is very high value. It is a high input impedance circuit, op-amp circuit. Okay, so it is assumed to be infinite to prevent any current flowing from the source supply into the amplifier's input circuitry. I in is equal to 0. When the input impedance is very high, the current flowing is 0. Okay. Real op-amps have input leakage currents from a few picoamps to a few milliamps. There might be a small leakage current, but the current ideally should be equal to 0 because the input impedance value is very high and ideally it is infinite. Okay. Then we'll see what do you mean by output impedance Z out of an op-amp. So here, according to our definition, if you see, the output impedance of the ideal operational amplifier, ideal op-amp, is assumed to be 0. So ideally, output impedance should be 0. It is acting as perfect internal voltage source with no internal resistance so that it can supply as much current as necessary to the load. Whatever load you are going to use as an application, it is going to supply maximum current to it. This internal resistance is effectively in series with the load, thereby reducing the output voltage available to the load. Real op-amps have output impedances in the 100 to 20 kilo ohm range. So here one thing you have to remember for op-amp, its input impedance will be ideally very high, infinite, and its output impedance will be ideally 0, very low. Okay. Then we'll go to see what is gain of an op-amp. Okay, so it is also called as large signal voltage gain. An op-amp basically amplifies the difference between the two input terminals. The voltage gain AD of the op-amp is defined as the ratio of output voltage to the differential input voltage. So we give AD, that is the voltage gain, equal to voltage output voltage upon the difference between the two input voltage. So here you can see this is how it has been written here. AD is equal to V out upon VID. So here AD, this is your voltage gain. So this is your gain, and V out is the output voltage, and VID is difference in the two input voltages, difference of the two input voltages, which is called as VID. Okay, so if you take a ratio of output voltage upon difference of the two input voltage, it will give you the gain of the op-amp. Means how much it is amplifying, how much is the output voltage with respect to difference of the two input voltage. It's a simple thing, and how many times it is going to amplify will give you the gain. Okay. Then we'll go to see what is gain bandwidth product. Okay. Now there are two ways in which you can define it. In the first way, you can say it is the product of the open loop gain and the bandwidth at that gain. It is the product of open loop gain and the bandwidth at that gain, which is called as gain bandwidth product. Or for a closed loop, the gain bandwidth is the bandwidth of the op-amp. Okay, just see here, the gain bandwidth is the bandwidth of the op-amp when the voltage gain is 1. Because for a closed loop, you can reduce the gain, and when the voltage gain is 1, then whatever bandwidth of the op-amp is there, okay, whatever its frequency response are going to give you a bandwidth when the voltage gain is 1, that bandwidth itself will be called as gain bandwidth. Okay. Then we'll go to see what is slew rate. Okay, so there are two ways to define the slew rate. In first way, we will define it as the slew rate is the maximum rate of change of output voltage for a step input voltage. Otherwise, you can also define it as the maximum rate of change of output voltage per unit time. Just understand this. It is the maximum rate of output voltage of an op-amp per unit time, which is expressed in volts per second, per microsecond. Volts per microsecond. So it is a maximum rate of change of output voltage per unit time, which is expressed as slew rate. Okay. The slew rate makes the output voltage to change at a slower rate than the applied input. Eventually, the output waveform is a distortion of the input waveform. The typical value for the slew rate is 0.5 volt per microsecond. Okay. Thank you, students. These were the parameters of OPAMP.